This is the first and only video on section 4.3, continuity of vector functions. And so we're going to look at a definition and a couple of theorems, and these should not be very surprising given the videos from section 4.2 and what you recall from Calculus 1. So our vector function is continuous at C if for all epsilon greater than 0, there's a delta greater than 0, such that the magnitude of f of x minus f of c is less than epsilon whenever the absolute value of x minus c is less than delta. And so remember, this is how we're going to measure our distance in v sub n. And again, in my notes, I wrote f was a function from r into r3. Really, that should be v3, or actually just in general, some v sub n. And you'll notice that for f to be continuous at c, it has to be defined at c. So here we're not insisting that x and c be different. So the difference between the limit definition and the continuity definition is we don't have the insistence that the absolute value of x minus c be greater than 0. So we had a similar definition for continuity in Calc 1. Now, here's something nice. Theorem 93. Theorem 93 says, let's suppose we take a function and we define it in terms of component functions right here. If all of your component functions are continuous at C, then your function is continuous at C. So wherever each one of these are all continuous, this function will be continuous at those same places. Remember, f is a vector valued function. It takes a real number. In this case, we take our variable t, and it makes a vector. Then we have something very similar to what we looked at in Calc 1. Now, if you look at your notes, Theorem 94, I have it broken into 3 parts. But all 3 of those parts are basically summed up by the third. That is, f is continuous at c if and only if the limit and the function value are the same. So with the 3 parts is your function has to exist there, the limit has to exist, and the 2 have to be the same. But you can sum that up with just the third one. So a function is continuous at c if and only if the limit and the function value are the same. That is very similar to what we did in Calc 1. It's just that in Calc 1 we had real valued functions. Now we're dealing with vector valued functions. And I'm going to say this again. You can think of the real line as v sub 1. So you can think of the real line as one-dimensional vectors.